chemistry of the soils needs some analysis too. So all of a sudden, you have the biologist, the chemist, the geologist, the astrophysicist in the same room talking to one another. And you know something? Before the day is out, we are publishing papers together. And so the origins of life, the origins of planets, galaxies, the universe itself, is inherently cross-disciplinary. And for that reason, for me, it is one of the most exciting ways we can explore the world around us.
You just talked about life elsewhere in the universe that belongs in a discussion of origins, not just human origins, but origins of life in general. I want to ask you about that, but before that, what are some of the big new discoveries when it comes to our origins and the origins of the universe?
I'd say the snazziest one, which really only recently reached consensus, was the account of the origin of Earth's moon. Earth's moon is an enigma because an object that size, we have a relatively large moon. It's one of the largest in the entire solar system. An object that size and round ought to have an iron core, because when you make objects in the solar system from the birthday ingredients of this part of the universe, you have a certain amount of hydrogen and helium and carbon and a certain amount of iron. And when you're in a gaseous state, figuring out that you have gravity, the heavy stuff falls to the middle, and the light stuff rises to the top. And so the geologists would call this differentiation. So an object like the moon would be nicely differentiated with a big iron core and lighter things as you move to the surface. Well, you look to the moon, and we didn't know this until we sent astronauts there, and they hauled back rocks for a laboratory study. What we learned is that the moon has hardly any iron for an object of its size. And that forced people to scratch their heads. You see, how do you make something that size with no iron? Well, it would have been made in the early solar system, and now we learned that the early solar system was a shooting gallery. It wasn't just 9 planets forming in tranquility. There was debris slamming into objects that were trying to become planets, shattering them into pieces again. Plus, there were comets that carried water and organic materials from one planetary surface to another. It was an interesting and active and enriched environment. Now, you go back to the early Earth. With the power of computers, we have come to learn that an object the size of Mars, if it's slammed into Earth, kind of sideswiping it, it could cast countless tons of Earth's crust into orbit around the Earth, which would then coalesce to form the moon. Now, Earth was already segmented into heavy materials in the middle and light ones on the surface. So if you carve a new planet from Earth's surface material and mantle material, you're not going to get a lot of iron. And so once this idea took hold, by the way, it required an understanding that the early solar system was a shooting gallery. It required moon rocks brought back by a funded Apollo program. It required the power of high-performance computing. All that had to come together. And once it did, we saw that, hey, this is actually pretty easy to do. And, in fact, recently we opened a space show here at the Hayden Planetarium called Cosmic Collisions. And the money shot in that space show is we recreate, using the latest data available, the collision between this Mars-sized protoplanet and Earth in the early history of the solar system. And you watch these fragments coalesce into what would then become the moon. That's the origin of the moon. In fact, we're on to the next problems now. So that's a triumph of multiple branches of inquiry coming together and arriving at a new understanding of our place in the cosmos.
You spoke a few moments ago about life elsewhere in the universe. The great Carl Sagan seemed to think there could be life elsewhere, even if he was a skeptic about things like alien abductions and UFO sightings. Where do you stand on that question?
When I look around on Earth and see that it's teeming with life, and then I look out to the universe and just see how large the universe is. You know, our sun is one of 100 billion stars in our own Milky Way galaxy, and the Milky Way is one of 50 or 100 billion galaxies in the universe. You multiply those two numbers, you get upwards of 10 to the 21 stars in the known universe.
Such staggering numbers that you're working with every day. I don't know how you wrap your head around them.
Well, you know, one of my favorite ways to do that is to find other things that have similarly large quantities. So, for example, that number 10 to the 21 is larger than the grains of sand in 1,000 beaches. It's larger than all the sounds and words ever uttered by all human beings who have ever lived. And so you can get other numbers that you might have some sense of or some deep respect for because of their size, and then you slap on another 3 orders of magnitude, and then you realize how truly staggeringly large the universe is. Now, here's my biggest supporting argument for the likelihood of life in the universe. Look around at the ingredients of life. Rank them in order. What's the number one atom in the human body? It's hydrogen, of course, bound with oxygen in the water molecule. What's the number 2 atom? Oxygen, bound with hydrogen in our bodies. What's the number 3 atom? Carbon. What's the number 4? Nitrogen. In that order. You say, okay, now you want to think life is special, let's look around the universe and prove to ourselves that we're made of special ingredients. And we look out in the universe, the number 1 ingredient is hydrogen, just as it was on Earth. The number 2 ingredient is helium. Well, that's not in life on Earth. Well, there's a good reason for that. It's chemically inert. You couldn't do anything with it even if you wanted to. So you can inhale it in parties, and sound like Mickey Mouse. That's about it. It's pretty safe to inhale because it doesn't interact with your biochemistry, except if you only inhale it, then you just suffocate. So let's put a pin in that, pull it aside. So the next ingredient in the universe is oxygen, just as it was in life on Earth. Next is carbon, just as it was on Earth. Next is nitrogen, just as it was in life on Earth. We are not made of exotic ingredients. We are made of the most common ingredients in the cosmos, 1 for 1. And not only that, you can make more kinds of molecules with the carbon atom than all other kinds of molecules combined. So if you take a step back and look at the periodic table and say, what is my most fertile element to experiment with? You're going to reach in and grab the carbon atom. Life as we know it, is the most complex chemistry we've ever seen. In order to get complex chemistry, you need the capacity to make complex molecules. And the atom to enable that, at the center of it all, is carbon. So when you have these people trying to speculate about silicon life, that's okay. Let them do it. But you don't need to do it because carbon is so fertile, and carbon outnumbers silicon in abundance of atoms in the universe. And if there's any chance you're going to get life, carbon will be there for it. And another thing on Earth, do you know how fast life took hold? Back when we were in school and you learned about how long it took to make life, you first had to know when to start the clock. And so they said, well, Earth was formed about 4.5 billion years ago. Okay, start the clock. When is the first sign of life? The earliest fossil record. It's about 3.6, 3.7 billion years ago. Subtract those two numbers, you get about 700 million years. That's not too bad. It's not billions. And so many people said life took hold relatively quickly. Might have had some fits and starts originally, but it was inevitable, just given a fertile enough pot of soup. Do you know life took hold faster than that? Because with our computer analysis of the formation of the solar system, you know what we now know? The early solar system was a shooting gallery. It's not fair to start the stopwatch the moment Earth formed, because Earth was continually slammed by asteroids and comets, making it sterile for the formation of complex molecules, because it was hot. So it's not fair to start your stopwatch back then. Wait till things cooled down a bit. You know how long that took? 600 million years. Earth wasn't cool enough to form complex molecules until about 3.9 billion years ago. Now you start your stopwatch. When does life take hold? A mere 200 million years later. Now you're talking fast. And so you combine the fact that we're made of common ingredients with the fact that life on Earth took hold almost as fast as it possibly could have. You can't help but declare that the universe must be brimming with life, because Earth had no trouble making it here on our surface, and possibly even deep beneath the surface, even if at the moment we have challenges coming up with life in the laboratory.
Dr. Tyson, in your work in public science education, you deal with the kinds of things we're talking about today. You deal with them every day, day in, day out. Some of the things that you teach run right up against central beliefs of our culture. I'm talking about beliefs like creation.